Okay, so the last speaker of the session here today is Tancredi Schettini Gherardini, who will talk about exotic spheres and Kaluza-Klein formalism.
Thank you. And first of all, thank you very much to all the organizers for giving me the opportunity to speak at this wonderful conference. Now, I'll be speaking about exotic spheres, and this talk will be based on these two papers. So the first one is from last year, and the second one hopefully should be out in a few weeks, and it's ongoing work with David Berman and Martin Sederbaum. Now, the talk will be organized as follows. The first 5 sections will be on the results contained in the first paper, kind of introductory, and then the last 4 will be on the new results. And as Dario rightly pointed out, I have many slides, so let's get started quickly. Now, the background, what are exotic spheres? Now, these manifolds were invented by Milnor in the 50s, and they are total spaces of S3 bundles over S4. Now, their key property is that they are homeomorphic to the 7th sphere, but they're not diffeomorphic to it. And it's the first time that 2 manifolds with these properties were found in mathematics. And since then, many other examples of exotic manifolds have been found. By exotic, I mean exactly 2 manifolds which are homeomorphic, but not diffeomorphic. I don't have time to speak about other examples, although they're very interesting. What I will do is kind of try to capture the essence of exotic manifolds with this picture. So the key thing is that 2 exotic manifolds are indistinguishable in the sense of topology, so they're homomorphic. But as soon as you put a differentiable structure on them, then the 2 are incompatible with each other. And so this is kind of a fundamental difference which comes way before putting any metrics or any form of geometry on your manifold. But yeah, now this is all maths. Now let's talk about physics. Why are they relevant? Some of the properties of these manifolds are that they are 7-dimensional, they are compact, and they admit a spin structure. This means that they are suitable candidates for compactifying 11-dimensional supergravity. And moreover, mathematicians have shown that they admit many, many Einstein metrics, although their proof is non-constructive, as it's often the case. So there is no prescription for doing that, but they exist. And this is yet another reason for why they might be considered in this context and give some interesting results. Now let's see what they look like in practice. I'll first tell you what they are not. So exotic spheres are not Coase spaces, they're not naturally embedded in R8, and they're not principal bundles. Now I'm saying this because in these 3 categories, you have very well-known techniques to construct the metric and study its properties and so on, but this does not apply to exotic spheres. They are quite close to belonging to the 3rd category though. So they are bundles, they're non-principal, and this makes things a little bit more complicated, but I'll show you how this still allows for a good formulation of a nice metric on these manifolds. Now let's see what they are in practice. So you have to take S4 as your base space, and then you can think of it with the usual stereographic coordinates. So both coordinates are just R4, and you have to employ the isomorphisms between R4 and quaternions, which is a natural one. And then you can do a similar thing for the fiber. The fiber is S3, and so it can be put into one-to-one correspondence with the unit quaternions. Now, using these 2 isomorphisms, you can write down this defines the whole bundle because it's a transition function, and I'll spell it out for you. So any point in the bundle in some local trivialization will be given by a point in the base and a point in the fiber. Now, under this transition function, Z is mapped to 1 over Z, and this is simply the inverse stereographic projection. So nothing is going on the base. It's 2 coordinates representation for the same point. Now, on the fiber, you have a non-trivial action. That's where the twisting takes place. And Y is mapped this thing. So it's multiplied from the left by Z to the H, from the right by Z to the L. And so here is quaternionic multiplication. And everything is normalized because elements of the fiber should be mapped to other elements of the fiber. And now this thing means that the structure group is SO4 because quaternion acting from the left with the quaternion acting from the right, together they define the group SO4. Now this is a structure group, and the key ingredient in this whole construction is the fact that the fiber is a quotient of the structure group. So the fiber is S3, so it's SO4 quotiented by SO3, and this will be key later. Now these 2 integers, H and L, they're very important. They classify the bundle. And what Milnor was able to show is that when their sum is 1, then the total space is homeomorphic to a topological 7th sphere. But when this other condition is met, it cannot be diffeomorphic to it. So when both conditions are met, we have exotic spheres, and the simplest case in which this happens is this choice of integers, h equals 2 and l equals -1. This has a special name, is the Gromov-Meyer sphere, and I'll be focusing on this. So I'll ask you maybe to remember these two numbers because they will show up in the construction later. And what has Kaluza-Klein to do with this? So this is the kind of usual equation for Kaluza-Klein in 5 dimensions, although usually physicists write it from right to left, because usually you have some higher dimensional metric, you want to decompose it into lower dimensional objects over there. But mathematicians, most of the cases, think of it the other way around. So they have some ingredients in their bundle, for example, some metric on the base and some connection, which is a gauge field. And this is a prescription of how to combine them to get a well-defined metric on the total space of your bundle, which also has some nice properties which we don't care about. Now, the idea would be to actually use the same technique for exotic spheres. So start from lower dimensional ingredients and build up a metric on the total space. I'll first review the principal bundle case because it gets us closer to where we want to get. Now, the ingredients here are quite simple. You have some metric on your base space. You have some metric on your fiber, just for convenience I'm giving it in non-coordinate basis. And then you have some connection on your bundle, which for us physicists is just a gauge field. And you can combine these 3 ingredients in such a way, and what you see here is a well-defined metric on the total space of your bundle. And it has those nice mathematical properties that I was talking about. And there is a very nice example for those of you who know it, which is if you take the base to be simply S4 with the usual round metric, the fiber to be S3 with a round metric again, but in Balbine coordinates. And then if you take the gauge field to be the SU2 single instanton, the standard thing, then you end up getting the round metric on S7. This is kind of the Hopf vibration from the physicist point of view. So these ingredients combine you to give you the round metric on S7. And for the case of exotic spheres, there's a subtlety which needs to be considered because they are associated bundles. They're not principal bundles. So some ingredients stay the same. For example, here the metric on the base is the same. Now notice that for the metric on the fiber, I have changed the indices from ij to this alpha beta. And the reason for that is because now the structure group and the fiber have different dimensions, because the fiber is a quotient of the structure group. And so I have this I here, because the gauge field lives in the algebra of the structure group, but it will be a different index from that, because the fiber will be smaller in terms of dimensions. And these 2 indices kind of talk thanks to this matrix, which intertwines the fiber and the gauge field. It has also a geometric interpretation, but that's not important for us. And you get, once you have these ingredients, this combination, which defines a metric on the total space. And now what I worked out in my first paper was just what are these ingredients for exotic spheres. And I'll show you here. You can take on the base, the usual round metric, and on the fiber, the usual round metric. Now, for the gauge field, you can use this isomorphism between the algebra of SO4 and the 2 copies of SU2. So you can split the index, kind of, into one field, which I'm just gonna take it as the anti-self dual instanton, and the other field, which is much less common to see, is the k equals 2 instanton. Why did I choose these 2? Because to reproduce the exotic spheres, if you remember, we had 2 integers, h and l. One was -1, the other one was 2. And these are exactly the winding numbers of these objects. So these are the key objects that define you the right twisting on the fiber. And then just to show you what it is, I'm putting here the expression for this K matrix, which intertwines the fiber and the structure group. Now, this is not important. What I want to convey is that it's a bit ugly, but I'll show you a nice way of kind of writing in a more compact form. Now, the properties, by definition, basically, the metric that I just showed you solves the Kaluza-Klein reduction of the action. By that, I just mean you integrate over the fibers, and what's left solves the Einstein equations in 4D. But solving the whole thing in 7 dimensions is a much more complicated problem, and actually it's an open problem. So we don't know if metrics of those family that I showed you actually can be Einstein or not. Now, some natural questions are, can you actually find a better form for the double instanton, or k equals 2 instanton, which you saw it's much more complicated than the k equals 1 case. Then another one is, can we study better this metric in terms of isometry, Ricci tensor, and so on? And then also a final one, which is probably the key one, can you actually turn on some fluxes to support this metric and give a full supergravity solution? Now, this is where my talk used to end after my first paper, because this is where all the results I had. And I kind of gave this talk in various places to try to convince other people, and myself as well, that exotic spheres were not that hard after all, and you can make some further computations. And in the end, two people kind of joined this journey, which are Martin Sederval and David Berman, my supervisor. And together we decided to set up a different kind of research question. So rather than going straight to full supergravity, think about gravity first. Are exotic spheres allowed in GR? And what we mean by that is more simply, think about the simplest spacetime you can have. So where it's static and the space-like part is an exotic sphere there, sigma 7. Now the question is, does this spacetime obey the strong energy condition? In other words, is the Ricci tensor of this sigma 7 of the exotic sphere non-negative? And to try and answer this question, a key insight was given by Martin, who realized that quaternions make this whole game much easier and all the computations easier in terms of difficulty. Now, this is the old metric that I was showing you before, but it's in tensor components, so loads of indices floating around there. And if you don't remember how ugly K was, this is it. And so it doesn't look nice. Now, with quaternions, you can do much better than that. So suppose you want to write down a Weyl for it. So the E part would be just the four-dimensional part, the base, and the epsilon would be referring to the fiber. Now, you can, first of all, treat S3 as unit quaternion, as a unit quaternion, which is the isomorphism I was telling you about before. Now we'll write quaternions in bold for a few slides to kind of make sure that everything is clear. But yeah, using these isomorphism, things are very nice. On the base, there is really nothing going on. This is just a Weyl of S4. On the fiber, there is the usual twisting, but now it has a much more compact form. So here you have the Weyl of S3. You have one of the two gauge fields, because you see that the action of K on one of the two is trivial, so that one is left as it is. And then you have this conjugation with Y, which is a very nice way of implementing this ugly matrix. And so with quaternions, things, thank you, become simpler in this sense. Now, some questions which are natural to ask are, first of all, once you have this Weyl, can you calculate the Ricci, and can you get some properties out of it? And then also, what about the isometries? But before answering those, I'll show you also how the instanton side of things gets simpler. So the first one, B, is the gauge field of the usual K equals 1 instanton, irregular gauge. And this is the field strength. So you see that there is another nice compact form of writing them with quaternionic valued objects. For K equals 2, we have more moduli. So now the moduli are at both positions A and B, and there are two sizes, lambda A, lambda B. The expression is still not very easy, and more importantly, it comes in the singular gauge. Now, we have two natural questions after seeing this expression. One of them is, can you calculate the field strength? What does it look like? And the second one is, can we regularize it? Because it's very easy for K equal 1, but it's not that trivial for higher winding instantons. And another one is, can we choose a specific point in moduli space so that this thing becomes nicer, more symmetric in a way? Now, let me start from the metric part to answer these questions. The first question was about the Ricci. Now, this is the Ricci. And the key object that appears in there is this difference of the two field strengths, where one of the two is conjugated by these Y's. And so we already answered another one. So we need to calculate this field strength for K equals 2. It is a necessary step. Now you can take contraction, and once you contract, you get the Ricci scalar, which agrees with the literature. Regarding isometries, there are things that are a bit more complicated. Now, mathematicians have proven that this is the maximal isometry you can have for an exotic sphere. So the first thing would be, we want to aim at that, find the metric with that isometry. Now, this should not come as a surprise. If you do X-dependent, which means base-dependent isometries on your fiber, those act as gauge transformations. And that's basically the essence of Kaluza-Klein theory, so nothing special there. While this is less known, but it's very important, so when you do isometries on the base, in our case it's SO5, because the base is S4, well, those kind of make your gauge field and field strength transform non-trivially. And I'll come back to this in the context of instantons. This means that the moduli space of instantons is not actually the moduli space of the Kaluza-Klein metric. Because when you act with your isometry, you're moving in the modular space of your instantons, and so you have to quotient out by the action in order to find the real modular space of your Kaluza-Klein metric. And just to show you, this is what happens for the single instanton case. So the position of the instantons transforms like that, the size transforms like that. The expressions are not important. What matters is that you have a fixed point. So if you choose position equals 0, size equals 1, then this is a natural choice. For the k equals 2 case, there is no fixed point, and the action is much more complicated. But we found a very nice point in the modular space, which is the sizes being equal, and the positions being both real and one opposite with respect to the other. And when you make this choice, you can actually calculate the field strength for the k equals 2 case. Now I'm going to just flash the expression. Then you can regularize it, and you get something else. And here, the only thing that I want you to notice is that there is this imaginary part of x and its modulus appearing over and over again. So you will probably believe me if I tell you that there is this symmetry here, SO3 symmetry in the rotations of that imaginary part of x. So it's not immediate, but you can kind of see it. And then something which is more subtle is that if you act on this instanton with a subgroup of the isometries, you're effectively you're enforcing gauge transformations, basically. And these gauge transformations can be undone by the isometries of the fiber. So you can combine these two things, and SO2 becomes indeed another part of the isometry group, which means that we have found the maximal isometry, SO3 times SO2. Now, just to summarize, I've covered all of that. Now, the Ricci, I gave you an expression for. The field strength for the k equals 2 instanton, I gave you an expression for as well, and it could be regularized as well, which was important, otherwise we would have got a singular metric. Then, basically, we identify the special point in the moduli space, which give you the maximal isometry that you can have, and you cannot have anything bigger than that. Now, the big question, which I said at the beginning of the second part, is, now, is the Ricci tensor non-negative? And we've shown, now it's just a matter of checking the eigenvalues and so on and so forth, that for this special choice of modular space for the maximal isometry metric, you indeed get a non-negative Ricci tensor, which means that we answer yes to our original question. And this is just a kind of a summary of what we've done. The thing is that this calculation, the result is nice, but also the intermediate steps give you the tools to apply these exotic spheres geometry to possibly the supergravity setting to find these famous fluxes which might support this solution. And thank you for your attention.
Check. Okay. Thanks for the nice talk. So I wanted to ask, there's these Brice-Korn singularities. They're like Calabi-Yau-like singularities, and if you have a sphere that links with them, that gets you a Sasaki-Einstein metric on exotic spheres. Why don't you consider that explicit?
For two reasons. One is personal, kind of, I found that to be more natural in the context of supergravity. And and the other one, so as you say, also that's the context in which they prove the existence of Einstein metrics. But I think that probably for a numerical study would be easier, but analytically it seems to be a bit harder with the presence of singularity and stuff. But maybe we can talk about that better. Mainly it's kind of, I guess, up to taste and preference. I think that this one is, I have a better analytical grasp on all of these formalisms.
Okay, thanks.
It will be possible in general.
Sorry, I had a question which is related to that, so let me ask that. So there is an Einstein metric, which is, I think it's an exotic sphere, and it, as far as I remember, has isometry SO5 cross SO2. So I'm not, did you say that they proved it's SO3 cross SO2?
Yeah. At least
I don't seem to agree with that. But
I don't think it's an exotic sphere because it's a coset. Is this the one that has a killing spinner, like n equals 1 supersymmetry?
Yeah, the V52.
Yeah, that's not an exotic sphere, I think.
What is the definition of an exotic sphere? I mean, this that
Müller
has the same cohomology up to and homology up to torsion. So what?
Yeah, the thing is
of S7.
I think the very definition is.
I think it's something that this of Milner where he showed 28 or something.
Yeah, it might be something that is actually diffeomorphic to the seventh sphere, although it has a deformed kind of seventh sphere. That's
Okay,
what
so
it might
another
be.
thing to talk about after the talk. Okay, sorry about this interlude. More questions?
I was going to ask if one can show that any of these have killing spinners or whatever the mathematicians call killing spinners.
That's a very good question. Unfortunately, I have a very unsatisfying answer for that. I don't know. This literally up to, we got up to here with what we've done, so there's definitely many directions to explore. I don't know about that.
So, sorry, but if they don't know what is Einstein, how can they hope to know if it's even, I mean...
You can be whatever. You can be Sasakian without it, whatever.
Yeah, yeah.
Well, that would...
Cone can be Taylor without it being whatever.
Yeah. Another related question. Of this list with the L and H, etc., there is no known example of Einstein metric. It's an open problem. You mentioned.
There are some constructions which refer to these Brigson singularities, which clearly they can be shown. So I think the thing is with this kind of Milnor construction, you don't get all exotic spheres. You get 15 out of 28 because there are 28 in total. And with this other Brigson construction, you get all of them. So the thing is, I don't know exactly if the one that they've used in the computations are of the same subset that are covered by this Kaluza-Klein thing. So this Kaluza-Klein doesn't apply to all exotic spheres. There are some which are outside of this family of metrics.
Yeah, okay. We have more time for more questions. There is one up there.
This is just a general question about these exotic spheres. So these K and L,
yeah.
And what kind of indices are they? What indices?
You mean H and L, the ones here?
Yeah, sorry, H and L.
Yeah, these are integers, and basically they also they classify the third homotopy group of the structure group. So the third homotopy group of SO4 is labeled by two integers, and these are the two integers. And it's basically the winding of SO4, because SO4 has the same homotopy group as SU2 times SU2. So each SU2 has a different winding. And so, for example, this would be the winding of the double instanton, let's say, and this one would be the winding of the single instanton. Yeah.
Please come forward with more questions. There, one.
Hi. The mathematicians talk about the group of, the collection of exotic spheres having a monoid structure and all that. I mean, so can you give a physical interpretation of any of that? Like, for example,
structure?
these things, if you do enough connected sums, it should come back to the standard sphere.
Say again, which structure then?
These exotic spheres are known to have a commutative monoid structure under connected sums, right?
Right, yeah. I'm not the right person, unfortunately. I'm a physicist, after all. But
Right.
I don't know about these connected sum things.
And also mathematicians, Milner says that there's a homeomorphism from this to the standard sphere. Can you take the field configuration you have here and then pull it back somehow to the normal sphere so as to have a... Does the fact that it's an exotic sphere play an interesting role in the physics? Or is it just an interesting example of space?
That I don't know. It's a very interesting question, the one of, at this point, there is no mention to the fact that it exists a homeomorphism, but it is, so the short question is not investigated in this work, but it's definitely an interesting question, and there are some explicit homomorphisms which are given between standard sphere and exotic spheres, and once you try to write them in coordinates, you get some discontinuity of some sort. So the physical interpretation is very speculative, so I can't comment on that.
Okay, I think I was too generous for asking for more questions. It has been pointed out that we are late, so we stop here. Thank again to Tancredi.